Thanks for the introduction. Thank you for the welcome. So I was thinking, what can I talk about? And the idea behind this talk is to sort of say functional programming, but interpret it in slightly different way. So it's what would functional programming be in an alternative universe? And if I just called the talk functional programming, well then, first of all, they would probably tell me that I'm silly, because what's the point of talking about functional programming in front of an audience where everyone does it? So I changed the title to Functionalist, following the sort of name that people sometimes use when they talk about functionalist architecture. My name is Thomas, and I'm sort of double affiliated. I'm recently started at the University of Kent in the UK. So my background is sort of functional or programming language research, and I do quite a lot of F#, and I'm part of the F# Works team. So I thought I'd say a few words about myself, because somehow I got invited here, which is very nice, and I've been sort of following some of the interesting things that have been happening in the Scala world, but I'm not really a Scala person myself. My background is I've done quite a lot of work on the F# programming language, which is the sort of cousin of Scala in the .NET world. And I think yesterday Martin said that Scala is sort of taking the merging the object-oriented with functional, and F# has always been merging the functional with object-oriented. So F# sort of tends to be a bit more on the functional first side, but otherwise I think we have sort of many common and shared themes. I've done some work on something we call theory of co-effects, which is effects track what your program does to the world, co-effects track what your program requires to the world. You can find it online. There's a PDF paper with lots of crazy equations in it. And I've also been working on type providers, which I'll show later on, and that's a sort of neat way of working with data in statically typed functional languages. And I'm sort of on the side, I'm also interested in philosophy and history of science, philosophy and history of computing. So this talk will sort of pick random things from all of those themes. I'll say a few things about some of the interesting F# features. I'll say a few things about type providers, because I think that's one area where F# has something really neat. And I'll link it together with sort of more philosophical outline. So what does functional mean? When you talk to functional programmers, they'll say, well, function, that comes from mathematics, and function from A to B is an object f such that for every A in the input, it's uniquely associated with some object f of a in the output. So that's a mathematical definition I stole from Wikipedia, I think. And that's what a function is, and sort of functional programming is really built on this idea that we compose functions and so on. Now, there's very different way of thinking about functions. So in architecture, Bauhaus is sort of school of thought that really sort of made popular the functionalist architecture, where a function is the purpose for which something is designed or something exists. So when they talk about functions, this is what they mean. And I think this is actually really sort of a useful interpretation, and it's useful to think about function in this sense. So what I'll try to do in the talk is to rethink some of the things we say about functional programming, but thinking more in this context. Now, you might say, well, this is really a vague definition, and function in mathematics is a formal, precise thing. But that's just because there's sort of multiple different kinds of knowledge. So some things you can describe precisely mathematically, some things you just can't. So this is as good as you can get with explaining what a function in this context means. And one of the really influential ideas from the functionalist or modernist architecture is that form follows function. So once you sort of understand what's the purpose of a building, or in our case, a program or programming language feature, the way it actually looks, the way it's sort of implemented, has to follow that function, that purpose. I'll have a few examples of that in sort of both programming and illustrated by some architecture. So even if you don't care about my program and code examples, you'll still see some pretty buildings in the slide, so that's still good. And the first theme I want to talk about is transformations. So this will be something very, very basic. And in functional programming, you're very often writing some data transformations, where really the point is to transform one value into some other value using a series of operations or transformations. And I'll just give you sort of brief example here using F#. This is not really new for anyone, because I'm sure you're doing the same thing all the time. So it's more to sort of show you what my environment looks like and how I do things here. So I've got, this is running in Visual Studio Code, which is sort of Atom-like lightweight editor. And I'm using Ionite, which is an F# plugin for it, which actually has been built by the community and has been maintained by the community. And I preloaded some data here, and just to show you how F# feels, this is a sort of data set with British pound to dollar exchange rates. And F#, very, very many things in F# are written using this pipe operator, which lets you do transformations. So I can say things like, for every price, give me the conversion rate, and I can run it interactively, and at the bottom, you'll see my conversion rates. I could say things like seek filter and check that the date is, what can I do? Yeah, I could sort of say, maybe give me the cases where this was more than 1.5, if there are some cases like this, and then give me the date in a nice short date format. And if I run it, it was never over 1.5, so let's do 1.45, and then I get a few days here. Now, I think one of the really nice things that I like about this way of programming is that you're very often doing things interactively. So I've been sort of running some code, testing it, see what I get, and you can do quite a lot of programming in this style. So I have slightly longer example where I take my exchange rate, and I'm using a function called pairwise, which will sort of go over the list and give me pairs with the previous and the next one. So I can compare how the exchange rate sort of changed between 2 days, and then I'm looking at cases where the exchange rate on the day after dropped by 0.02, and I get all the dates. And there's quite a few of those, but if I change it to say, so is there a case where it dropped by 0.1? And there is one date. So I do this just to show you how Brexit is a great idea. All right, so this was one example of working with data. And here I was using sort of plain lists, but the really nice thing about the pipe operator and this way of writing code is that it really works on a lot of different things. So I've got another example here, and let's see. I'll just show you a preview. You don't have to see the values, but this is a data frame which has lots of different information in columns. It's like a CSV file with some data about Titanic passengers. So it's sort of typical example data source that everyone talking about data science uses. I can take this and do the same sort of transformations over not just a list of numbers, list of values, but over an entire data frame. So this is using one library where I can say group rows by sex. So sex is a column defining whether the passenger was male or female. And then I can do an aggregation. And here you'll see sort of aggregates over all the numerical columns in the data frame. So with these just 2 lines, I can say that, for example, here, the average age of male passengers and female passengers was 30 and 28. And you can sort of see how much they paid as well, that sort of stuff. So really the sort of interesting idea here is that transformation is such a common theme in functional programming, and it takes multiple different forms. And I think in sort of architecture, you can see that there's quite a lot of cases where similar form gets repeated over and over again. So this is one building in Prague and another building from Czech Republic, and they both have sort of very simple shape with sort of regular structure, and it's just repeating the same pattern that's very general and works for many different things. Now the same thing I think applies in functional programming. So quite different example of what I was showing you right now is this little sort of toy programming environment, which runs in the browser, and you can type things like fun.cube, and when it loads, if it eventually loads, it will render a cube in the screen on the right. Now the other thing it lets you is that you can transform those shapes, we'll see. No, I can't transform shapes. Maybe I can transform shapes a bit later. I'll get to transforming shapes later on. But the idea is, I'll show you some code sample first, and then I'll try to see if it works. The idea is that you can take a shape and you make a cube, you transform it, you change a color, you move it, there it is. So I have a cube. I'll make it bigger, and then I can say things like change the color of a cube to orange. And the idea is that the cube is just a value, some representation of what I'm doing, and I'm transforming it by changing color. Now, you can do more things. So this is an example where I take a cone, change the color of a cone, make it bigger. I'll take a cylinder, change the color, scale it to make it taller, and move it in one direction. And if I run it, then I created a little tower. And with few more lines of code, you can create things like castles. But really, the sort of interesting point here is that pretty much all I'm using, like the core thing, is just composing functions using the pipe operator, which passes the thing to the left to the thing on the right. And I think that sort of relates to this mission of the modernist design, where a lot of people try to eliminate ornaments from architecture. So this is how Art Deco buildings look in Brussels, and you can compare it with something like this, which is really sort of simple structure, just regular shapes, nothing that doesn't have to be there isn't there. And in programming languages, I think this relates to this sort of elimination of keywords where, and Martin was saying that yesterday, that Scala doesn't really have that many keywords, and it's something that F# shares as well. And when you look at the code that I was using for composing these shapes, it really is all sort of functions that are there for the meaning of the program, and none of the sort of extra infrastructure to do while loops or class definitions or type class definitions. It's really sort of focusing on what's the meaning that I'm trying to construct here. And the fun thing on the side is that the pipe operator, it's really just sort of an operator that takes the thing on the left, passes it to the thing on the right, and it's probably going to be one of the major contributions of the F# language to the programming universe, because it's now appearing in R. I think there's a proposal to add it to JavaScript. And in F# you can define it like this. So this is some sort of, I think, 9 characters of F# that actually people are interested outside of the F# community. So this says, define a pipe operator that takes X and F. X is some input, F is some function, and it calls the function on the input. So this is one interesting example, one interesting thing coming from F#. The other thing I want to talk about is type providers. And type providers in F# really appeared for this sort of, the function here is that we want to navigate through some data sources, and it could be a database or some web-based graph structure or a JSON file, navigate through a data source and extract some information from it. So I'll show an example. I have 2 examples here actually. Think I need this. Well, I do. So the first example here, I'll make this smaller. The first example, which I think really illustrates this idea nicely, is this World Bank type provider. Now, World Bank is a data source, sort of online, or well, World Bank is a institution that tries to help poor countries, but one of the things they do is that they collect a lot of data about countries, and they make this data available. And if you want to query the World Bank and find, say, the carbon emissions of Germany, you can go to their website. They have an API documentation. You issue some XML requests. You get some XML back. If you're lucky, you will find the data there. What I want to show you is a sort of a way of adapting this and making it really easily accessible from a programming language. So F# mixes the sort of functional and object-oriented style, so it has a dot operator, and if you type dot, you get a list of members that the object has. And the interesting thing here is that the type providers actually sort of give us a way of generating these objects behind the scene at compile time. So when I type dot, it actually had a look. It actually had a look at the data source, the World Bank service, and it gave me a list of countries that are all here. So I can say Germany, and I get Germany. If Scotland ever decides to leave the UK, I will type .Scotland, and when they're in the World Bank data set, I will have it here. So it's future safe. And the same thing happens with indicators. This is a bit of a challenge because my screen isn't too big, but the World Bank has lots of different indicators about countries, and we're making those sort of directly accessible through the members of the object. Now, nobody expects that you will actually type this from scratch because it tends to be long. The double backticks mean sort of make it a valid identifier no matter what's inside. But if you're using any decent editor, and everyone is, then you will actually be able to navigate through the data. So just to show you some fun data, this is showing the total carbon emissions of Germany in kilotons. So for Germany, it's actually going down. Now the scale doesn't start with 0 here, so my charting library is a bit confusing. But fortunately, this is not a data science audience, I hope. If we look at the United States, not making any political statements here. But the nice thing here is that I can really sort of access the data source through my programming language and through my programming language sort of native features. So this was the World Bank. Now, for World Bank, this is a type provider that's been specifically built for that one data source. So it makes for a wonderful demo, but otherwise it's not all that useful. And I'm going to show you another one, which is more interesting. And this is a type provider for accessing any JSON, XML, and CSV data structures. So I have a sample URL here, and this is a URL for Open Weather Map, which is a sort of service where you can register and get weather forecast. And I entered Berlin here as a city that I'm interested in. And if you wanted to use this in a statically typed way, then very often you have to do something like have a look at the response, see what the structure of the JSON is, write some records or case classes or classes to represent that structure. Then you can use some library that will load it into your types, and then you work with the types. Or you can just say, screw it, I'll write this in JavaScript, and you'll be done in 10 seconds. Because you just type .temp, and if it's there, well, then you win. If it's not there, you lose. What the type providers are trying to do is to give you sort of a nice way of having that JavaScript-like way of working with data, but in a statically typed world. So what I did here is that I defined a type called weather, which is created by a JSON type provider from that sample. And then this has some members. Most importantly, it has a, well, I'll do this a bit differently. So most importantly, it has this load method. And on the first line, I'm using the URL as a sample to guide the sort of type provider mechanism. And on the second line, I'm saying, now actually load this URL, whatever it returns, into an object and give me that object. And then I can say weather dot. And you actually see members that are generated based on whatever is in the JSON file. So it has information about the city. So let's see, did we get Berlin in Germany? We did get Berlin in Germany. And it also infers that this list thing is some collection of some other nested records. So I can say for weather in this list, do and maybe I'll just get the temperature during the day. So FSARP does also have list comprehension syntax, and I can say something like this to get a chart. And here's the weather forecast. It's the temperatures for the next few days. So looks like I came just when it's on the downer, on the sort of lower side of the spectrum, but it's still pretty good. The interesting thing here is that you can, so here I give the type provider a URL as a sample, and then I load the same one. So this is going to work probably fine, but typically you actually want to have some sort of function that takes a city and gives me weather in that city. So in the URL, I'll just put in the city, and then I'll return the data. And now I define a function, and I can say get temp London and draw the chart. And did I actually do this? Or did I do something wrong? Let's see. I probably did something wrong. No, my internet was slow. So here's the chart for London. This was for Berlin. So we might actually have a nice weekend in London. Woohoo! Now, the interesting point here is that I'm using a different URL as my sort of sample and different URL as my runtime input, and that's the sort of interesting potential issue, because if the service returned very different JSON structure for very different cities, then this wouldn't work, because when I do temp.day, this is generated based on the sample. But it just happens to be the case that whenever you're using a reasonable JSON service, they will have sort of similar structure for all different inputs. So this idea of inferring the sample, generating the types from a sample, actually works really nicely in practice. It always scares the type theory people, but that's fine. So this was the JSON type provider, and I think where it sort of fits with the functionalist way of thinking about design is that in functionalist thinking, the idea is that you sort of focus on the message of simplicity, using basic geometric forms and using simple materials. And if you look at the code I was writing, it really is just typing dot and selecting things. So that's where I think that the simplicity in the design really is working nicely. And it is using some sort of clever material behind the scene, because when I type dot, there is some sort of clever logic going on behind, where the compiler will sort of work with the type provider to figure out how exactly to get the data, how exactly to build the list of members. So there's something clever going on behind, but the form at the end is very simple. So it's not like you have sort of wiggly sort of things everywhere. It really is a sort of simple, straightforward shape, and that's sort of the dot operator in F#. So this is roughly the sample I was showing, and it's just navigating through an object. Now, one of the sort of interesting things that I think can happen both in architecture and design and in programming is when you have some interesting material, you can sort of test how far you can take it. And people definitely did that with reinforced concrete. So this is not, it looks a bit scary, but it's not too bad. But this is a pretty amazing building in Sao Paulo, where you can see that the entire, it's a gallery, and the entire thing is really just standing on these 4 columns in the corners. And it's pretty huge, and it is really sort of exploiting the fact that you can use reinforced concrete and it will not fall down. And I think you can sort of do the same thing with programming, where if you have some sort of nice, interesting mechanism, it's interesting to see how far you can take it. And so I'll show you one more example of a type provider that I've been working on. And this is actually not in F#. It's a separate project that is heavily inspired by F#. And the idea here is, can we make basic data exploration really, really easy, but keep it as a reproducible program script? So if you look at sort of media reporting on some data, they might use Excel and do some sort of pivot tables to aggregate data, and then they give you some resulting chart. And if they've done it right, well, then it's a nice chart. If they've done it wrong, then you will never find out because there's no trace. So here the idea is, what would be the sort of simplest possible web-based scripting language where people can write a little bit of code to do some data transformation. And the way it works is that you just use dot. So Olympics, in this case, is a sample data source I have with all the Olympic medals ever awarded. So there's what Olympic Games is it, what year, what discipline, and what medal the person won. And you can say dot, and it tells you, here's a list of available operations that you can do with the data. So I can filter the data and say, and again, I say filter data, and it comes up with all possible sort of conditions I can write, such as limited to specific Olympic Games. So if I say I only want Rio 2016, then it filters the data set, and I get Rio 2016 medals. And then I can type dot, and it offers more filters if I want it, or then if I want to do something else. Then I can say group data. So if I wanted to know what's the country with the largest number of gold medals, then I can group the data by team. And the other neat trick that this does is that it actually shows you a live preview of what we've created so far. So I can say group this by team and sum the number of gold medals. I could also do things like count the number of distinct athletes, and sort the data by the number of gold medals. And then you can see what's the aggregate. So United States do have the largest number of gold medals. They also happen to have the largest number of athletes involved in the Olympics. And it's sort of pretty simple data transformation, something you could write in an SQL query. But the neat thing is that the only language construct I actually had to use to do this was dot and selecting a member. So if I do a few more things, then I can say, now it gets awfully complicated because takes an argument, and I do need parentheses, but yeah, I haven't figured out how to do that one yet. So we can get a data series where the key is the athlete and the value is the number of gold medals. And then I have to do a bit more of real programming and say, create a column chart with this data. Maybe not. What did I do wrong? No, this is actually supposed to. So this is actually supposed to be compost, but let's see. I got annoyed by Word, which whenever you write composable, it always says, "Did you mean compostable?" And no, I didn't. All right, so this is the right way to do the chart. So you can use the simple sort of dot mechanism take it way further than I think was originally intended, and embed quite a lot using that simple form. So I sort of think that if dot in OO languages is concrete, then what type providers give you is reinforced concrete. Now, so this was two examples. One was the function composition, where we sort of eliminate all the ornament and all the keywords. The second was type providers, where we're using the sort of basic OO dot and member access and taking it a bit further. And the last thing I want to talk about is computations, and specifically FSARV has this feature called Computation Expressions, which I think is relevant to some of the sort of work on asynchronous, reactive, and concurrent programming that people have been doing in Scala as well. And it's also one of the areas where I think the two languages really sort of exchange ideas quite a lot. So what's the idea? What's the purpose? And I think this is also one case where really the sort of distinction between thinking about function as a purpose and function as a mathematical concept is pretty big. So if you think about function as a mathematical concept, then this is just going to be 20 minutes on monads. But if you think about function as a purpose, then I think you can get a really interesting sort of alternative view on what this language feature does. So what we are trying to do with asynchronous and concurrent computations in FSARV is to give an alternative meaning to an ordinary computation. And I'll show you an example. I think in architecture you often sort of have this as well, where the context really matters. So this is a housing complex in Prague that doesn't look all that impressive. But if you take the same sort of shape, take the same structure and put it somewhere else, then it really looks like a very, very different thing. So I think in the sort of next few examples, it's really a case of taking something very ordinary and keeping the structure but changing the meaning behind it. The example where this sort of first appeared in FSARV is when you need to do asynchronous computing. So this is a little FSARV code snippet defining a function try get page length, which takes a URL, then it creates some web client object, it downloads the URL, gets the HTML, and then it returns the length, and it wraps this in the sum constructor. So that's the option or maybe type that we're using to represent missing or failing things. So if it works, I return sum of length. If it doesn't work, then I return none to indicate that I don't know. This is really simple. The only problem with it is that it blocks the current thread when it does the download. So downloading will block and it might take fairly long time. And if you're doing these things in parallel, or if you're on a server, that's a very bad thing to do. Now, you could rewrite this using sort of callbacks and explicit continuations, or in JavaScript, people use futures. But it really changes the structure, and you can't do normal language things like try with to handle exceptions. The way FSARV does it is that you wrap the code block in this async block. So I'll switch between the two a few times just so that you can see where the differences are. So I wrap the code block inside this async curly brackets, but otherwise I keep all my sort of syntactic structures the same. The one more change that I do is that I have to add return. So that's just sort of syntactic requirement inside these computation blocks. And when I had download and let HTML equals that, I now have let exclamation mark HTML equals async download. So this let exclamation mark is what the mathematicians would call monadic bind, and it means sort of start this computation. When it finishes, resume this asynchronous workflow, and behind the scenes it runs the code so that it doesn't actually block the thread. But I think what I find really sort of nice about this way of writing the code is that you still keep all your normal syntax in this block. So try with. Previously, it was just sort of normal .NET exception handling. Now it does some uses some clever mechanism to propagate the exception handling sort of across the multiple possible threads that are running the code. So it's reinterpreting all the basic language constructs in a different context. And I'll show you one more fun example of this. So here, this is a sample. Previously, I was running F# on the .NET runtime, or it works on Mono as well if you're running Mac or Linux. It runs on .NET Core, which is the sort of Microsoft next version of .NET that's cross-platform. Now I'm going to do something different because, yes, this is typo. Because the only way I can do UI is in a web browser. So now I'm using F# through a project called Fable, which compiles F# to JavaScript. And so here, when I type something, I have a process running in the background, which will recompile my code, and it reloads in the browser. And you can use these async computations in a browser as well. So one example I can do here is to say sleep for 1000 milliseconds, and then change the color. And I'll start the computation immediately. And if I save this, it will stay for 1 second, and then the color changes. And if I wanted to do traffic lights, I could say something like this. So which way does it go? First we have green, then we do orange, and then we do red. And now I have a little sort of asynchronous traffic light, and it really works in the browser sort of nicely, because in the browser you can't block a thread. There's no way of doing that unless you're mining bitcoins or something. But then your UI will freeze, so that's not very good. So I created this sort of asynchronous computation that behind the scenes creates a timer, waits for 1000 milliseconds, change the color. But the really nice thing here is that you can still use some of the basic sort of language constructs, such as while loop. So now I created a traffic light that will run in a loop forever. And if you don't like copy-paste, you can say things like for color in this list of colors. Sleep, and then change the color. And it's still doing the same thing. And I really like this sort of idea that you can take normal sort of language constructs and just run them asynchronously. And when I sort of was starting with programming in Visual Basic, I always wanted to write a loop like this to run my game, and then it wouldn't work because you can't block threads, and programming was so hard. And it Still is hard these days. You still have the same problems you had in Visual Basic 4, but with async computations, it gets a bit nicer. Now, this is using async computations, and I think the sort of interesting design principle here is that the way this feature is implemented in F# is that it gives you fairly flexible material, and you can use this sort of async block. That's one of the standard library things, but there's quite a few other different kinds of computations that people are using or that people build, and if you sort of design those with the material in mind, then you can create quite a lot of nice sort of libraries, nice APIs that fit well with the idea. So this is sort of another interesting use of Concrete, where it really sort of was designed because they knew how they are going to build it. And there's things you can do with Concrete, like this. There's things you can't do with Concrete. So this is a picture from the Abu Dhabi Louvre Museum, which has this crazy roof pattern, and that's some sort of metal things bolted together, which I'm showing you this only because the guy designing the roof structure actually used F# to do some of the modeling. But you can't build this with Concrete, so then you need a different material. And I think in programming, what is sort of a useful design principle along similar lines is that when you have some right abstractions, it should either make things easy or it should make things impossible. There's one sort of really interesting asynchronous programming abstraction that people have been using in F#, which is called asynchronous sequence. And I think this is a really nice example of a design that is designed for a sort of clear purpose. It makes things that fit with the purpose really easy, but things that don't fit with the purpose, you will soon realize that there's no way this is going to work well. So what this does is that you have async seek, which is asynchronously produces async result. So the asynchronously produces just means you can start it and it will eventually call you back with a result after it does some I/O or whatever stuff. And the async result is either this sequence has finished, there's no more data in it, or it says, here's the value, and it gives you the value together with another asynchronous sequence that you can start again to get more data. So the type definition is pretty much sort of the functional programming textbook example of a list, of a linked list, except that it does every sort of step asynchronously to compute the next thing. And this is a sort of amazingly nice pattern for certain kinds of asynchronous programming. So I have a little example here where what we are doing is that we have some data files with some prices, and we have data for 1 year. So we iterate over the days of the year, and then we want to read the JSON data that we download. This is still running in the browser. So this is asynchronously sort of making a request to the server to get the data. Then we find the price and we display it, and we wait for 100 milliseconds. And I'm running this in an async block, just like before with the traffic lights. So if I can find the right window, Well, you can see that my parsing didn't work as expected. What did I do wrong? Well, I did something wrong. So I did something wrong, and rather than getting my data, I think I'm printing the wrong thing here. Yes. This is what I wanted to print. Almost value. All right. Now I'm sort of iterating over some data source, downloading the data one by one. You can see how this is happening if you open the debugger. Now, one really annoying thing here is that there's no nice way to break this if you're just using async, because async is a computation that produces one value, but here I'm actually producing a sequence of values. So what I can do here is I can define a computation read prices that will do pretty much what I had here. It will find the number and it will yield the value. And this is now a function that returns an asynchronous computation that will iterate over an input, read data one by one, and return them. And then I can consume this, and I can say for v in read prices, do this, and I need to change how I'm starting things, but otherwise it does the same thing as before. And I now have the same thing, but it's do I have the same thing? Well, hopefully I do have the same thing. But now it's sort of nicely separated the reading from the iteration. And the one nice feature here is that the consumer sort of defines how quickly the input is being consumed. So this is an abstraction that fits nicely with the idea that it really depends on what the purpose is. And if your purpose here is I want to consume some data asynchronously as a sequence, then this works well, but you wouldn't use it for things where you have sort of push-based reactive systems, because there you have no control over how you consume things. So to wrap up, if you look at what sort of modernism and functional means in the design world, then it means a couple of things. It means this analytical approach to the function. So that's really sort of trying to understand what's the purpose of the thing I'm building. Interesting use of new materials, and openness to structural innovation and the elimination of ornament. And I think those are really actually principles that we should be thinking about and using in programming, be it sort of language design or library design or actually building systems. And I try to give you a few examples in the talk. So the function composition that really sort of replaces this lots of different keywords with just simple, in my case, the piping operator, eliminates a lot of the keywords and the ornament. Type providers are taking a known structure, the dot and member access, and sort of changing what this does, but keeping the same simplicity. And computation expressions are letting you sort of repurpose an existing pattern and use it in many different ways. So it's sort of using the new material that the language provides in a sort of way that fits well with whatever the material is, but works in a number of different areas. So the whole point of the talk really was to sort of try to convince you that whenever we say functional programming, it's maybe more useful to think of this function as the purpose for which things are built, rather than function as mathematics, because functions in mathematics are great for proving things, but I feel that programming is very, very often more about the sort of design and building things that will be used by other people. And the one interesting principle that we can take from the modernist architecture is this form follows function, where the purpose for which something is built really determines what is the structure of it and how does it look. Thank you very much.